Thank you very much for the invitation. It's really nice to be in Lumini. Hyperbolic free-by-cyclic groups in many ways resemble the fundamental group of closed hyperbolic three-manifolds which fiber over the circle. And with Yael, Algom-Kfir, and Arnaud, Hilion, who's here, we use the Cannon-Thurston map to understand the difference between the boundaries of these groups. So I'll start with the definitions. Let Fn denotes the free group on n generators. And let's phi be an automorphism of the free group. Then define the free-by-cyclic group G phi to be the semi-direct product of the free group with the integers defined with respect to this automorphism. It's an H&N extension and has a presentation with each of the generators from the free group, a stable letter T, and the relations that T conjugates each generator of the free group to its image under the automorphism. So in fact, if little phi is an element of the outer automorphism group of the free group, and phi and C are automorphisms in the class phi, then the free-by-cyclic groups G phi and G C are isomorphic. In other words, you can define a free-by-cyclic group with respect to an outer automorphism, and to write a presentation, choose some automorphism in its class. Here's an example. The free group of rank 3 can be generated by the letters A, B, and C. And let phi be the automorphism that maps A to B, maps B to C, and maps C to the word AB. Every free-by-cyclic group can be thought of topologically as the fundamental group of a mapping torus of a homotopy equivalence from a graph to itself. So in this example, the free group of rank 3 is the fundamental group of a rose with 3 petals, and to form the mapping torus, take the product with an interval and glue the bottom to the top using a homotopy equivalence representing phi. So here, the loop A on the bottom glues to the loop B on the top, the loop B on the bottom glues to C, and C glues over A and B. And it follows from this construction that the co-homological dimension of a free-by-cyclic group is equal to 2 because the universal cover of the mapping torus is contractible. One approach to studying free-by-cyclic groups is to understand the correspondence between geometric properties of the free-by-cyclic group G phi and algebraic properties of the automorphism or outer automorphism. So one example of this correspondence is given by Brinkmann in 2000. He proved that a free-by-cyclic group G phi is delta hyperbolic. So it has large-scale negative curvature if and only if the outer automorphism phi is atoroidal, which means that no conjugacy class of the free group is invariant under a power of phi. The automorphism above is atoroidal, but suppose it wasn't. Suppose, for example, the element A was mapped to itself by phi. Then the mapping torus contains an embedded torus, so the group is not delta hyperbolic. And Brinkmann proved that this is essentially the only obstruction to hyperbolicity. Another example of this correspondence is given by Misha Kapovich and Kleiner in 2000. They proved that a free-by-cyclic group, G phi, splits as an H&N extension or amalgamated free product over the integers if and only if, the free-by-cyclic group does not split there over the integers if and only if no power of phi preserves a free splitting of the free group. No power of the automorphism above preserves a free splitting of the free group, but suppose it did. Suppose, for example, phi fixed the free factor A and the free factor generated by B and C. Then you can split the mapping torus along an annulus, which gives a splitting of the fundamental group. And again, they prove this is the only obstruction, or this is the only way a free-by-cyclic group will split over the integers. As a special case, we'll often restrict to fully irreducible outer automorphisms. So if phi is fully irreducible, which means that no power of phi, or no free factor of the free group is invariant under a power of phi. Then the free-by-cyclic group G phi does not split over the integers. So one problem in geometric group theory that was an underlying motivation for this project is to understand the quasi-isometry classes within the class of free-by-cyclic groups. Both the properties of being delta hyperbolic and the property of virtually splitting over a two-ended subgroup are quasi-isometry invariants for finitely presented groups. So some quasi-isometry classes can be distinguished, those that are hyperbolic and aren't, those that split and those that don't. However, among the delta hyperbolic free-by-cyclic groups which do not split over Z, there are no known quasi-isometry invariants. And this is still open, and one natural approach to this question is to try to understand the visual boundary of these groups. So recall the notation. If X is a proper geodesic metric space, then the visual boundary of X is defined to be the set of equivalence classes of geodesic rays in X, where two rays are equivalent if their Hausdorff distance is bounded. There's a natural topology on the space X union its boundary where two rays or segments are close if they travel together close to each other for a long time before diverging. And since X is proper, X union its boundary is compact. An important theorem in geometric group theory states if X and Y are delta hyperbolic proper geodesic metric spaces, and X and Y are quasi-isometric, so they have the same large-scale geometry, then the visual boundary of X is homeomorphic to the visual boundary of Y. In other words, the homeomorphism type of the visual boundary is a quasi-isometry invariant. The converse fails in general. However, there's a finer structure on the boundary called the quasi-conformal homeomorphism type, which is a complete quasi-isometry invariant, and the ultimate goal is to understand that structure. Although that won't come up anymore in this talk. And the last piece of background we need is a result due to Svina and Mess. So their work implies that since the conformal dimension since the cohomological dimension of a free-by-cyclic group is equal to 2, then if the group is hyperbolic, the topological dimension of the visual boundary of the group is equal to 1. So we're in a setting where a theorem of Kapovich and Kleiner applies. This is Misha. They prove that if a group G is delta hyperbolic, if the group G does not split over a virtually cyclic subgroup, and if the dimension of the visual boundary of G is equal to 1, then the visual boundary has one of 3 possible homeomorphism types. The first possibility is that the boundary of the group is homeomorphic to the circle. The second possibility is that the visual boundary of the group is homeomorphic to the Sierpinski carpet. And the third possibility is that the visual boundary of the group is homeomorphic to the Menger curve. And I'll just recall the Sierpinski carpet is homeomorphic to the space you get by starting with the unit square, removing the square in the middle ninth, and repeating this in each of the remaining 8 squares infinitely many times, and taking the intersection. And the Menger curve is similar, except that you start with the unit cube and remove the square prism from the middle ninth face, and repeat this on all of the sides, and take the intersection. So much more is known about hyperbolic groups with boundaries of the first 2 types. Combining work of Tukya, Gabay, Kassin, and Jungrace proves that any hyperbolic group with boundary homeomorphic to the circle acts properly and co-compactly on the hyperbolic plane. So in this case, if the group does not split, it maps onto some triangle reflection group with finite kernel. Kapovich and Kleiner, in the same paper, analyze hyperbolic groups with Sierpinski carpet boundaries. They prove that the group, together with a set of stabilizers of the peripheral circles in the Sierpinski carpet, forms a Poincare duality pair. And in particular, it follows from this work that the Euler characteristic of any group with boundary of the first 2 types is negative. you can easily compute the Euler characteristic of a free-by-cyclic group using the mapping torus and see that it's 0. So their theorem has the following corollary. If the outer automorphism phi is atoroidal and fully irreducible, so the free-by-cyclic group is hyperbolic and does not split over the integers, then the visual boundary of the free-by-cyclic group is homeomorphic to the Menger curve. However, this proof is somewhat indirect. It uses only the Euler characteristic of the group and does not tell you any more information about the large-scale geometry of the free-by-cyclic group. And moreover, since all of these boundaries are homeomorphic, the homeomorphism type of a boundary won't distinguish quasi-isometry classes. So with Yael and Arnaud, our goal was to explicitly construct some non-planar subcomplexes in the boundary to understand them better. And we prove the following. We prove if, with the same hypotheses, if phi is atoroidal and fully irreducible, then there exists an embedding of the complete bipartite graph on 3 vertices into the visual boundary of the resulting free-by-cyclic group. And we don't need this hypothesis, but I'll keep it for the talk for ease of exposition. So on the one hand, our theorem is a corollary of the corollary because every compact one-dimensional space embeds in the Menger curve, so therefore embeds in these boundaries. And on the other hand, this corollary is a consequence of our theorem. Once we've found some non-planar subset of the boundary, we can immediately apply the classification without the deep work of Tukia, Gabay, Casson, and Jungries to conclude the boundary must be the Menger curve since it's non-planar. We don't need fully irreducible to find some subgraph, but it will have cut points in the boundary. Okay. So before I explain what goes into the proof of this theorem, I want to compare the boundaries of these free-by-cyclic groups to the boundaries of related three-manifold groups. So I want to compare the boundaries of free-by-cyclic groups to the boundaries of a fundamental group of a mapping torus of a pseudo-Anasav homeomorphism of a surface of a surface. And there are 2 cases to consider. The first case is that the surface sigma is closed. Closed, connected, orientable, and has genus at least 2. And suppose C is a pseudo-Anasav homeomorphism of the surface, meaning it doesn't preserve the homotopy class of any closed curve on the surface. Then, as above, you can form the mapping torus defined with respect to this homeomorphism. And Thurston proved that this 3-manifold has a fundamental group which acts on hyperbolic 3 space properly and co-compactly. And in particular, the visual boundary of the fundamental group of this mapping torus is homeomorphic to the two-sphere. The other related case to consider is that the surface sigma has non-empty boundary. So the surface has free fundamental group. And suppose C is a pseudo-Anosov that fixes the boundary component pointwise. Then in the mapping torus, there will be some embedded torus coming from the boundary curve. So this is not a hyperbolic group. And since the fundamental group is free, C induces an automorphism of the free group, which is not atoroidal, but it is fully irreducible. So this free-by-cyclic group, G(C), which is the fundamental group of this three-manifold, still acts on hyperbolic through space, again by work of Thurston and Sullivan. But now the quotient will be some finite volume three-manifold with torus cusps. You can truncate along the torus cusps and take the universal cover to get a cat zero space with isolated flats. So in other words, the free-by-cyclic group here, G(C), is a cat zero group with isolated flats. So it has negative curvature away from the flats in the universal cover, which come from lifts of the torus boundary component. Work of Preska and Kleiner proves that the cat zero boundary of this free-by-cyclic group is well defined and unique, where the cat zero boundary is the visual boundary of this truncated hyperbolic through space. And Ruane proved that the cat zero boundary of this free-by-cyclic group is homeomorphic to the Sierpinski carpet. In particular, in both of these cases, we'll say that the boundary of the resulting mapping torus group is planar since it embeds in the two-sphere. And one of the main goals of our project was to understand what exactly are the mechanisms that lead to planar boundary for free group automorphisms that are induced on surfaces, and Menger curve boundary if they're not. So the main tool we use to study these boundaries is the Cannon-Thurston map. And the general setup is, suppose that H is a subgroup of G, and H and G are hyperbolic groups. Then choosing a generating set for H and extending it to a generating set for G yields an inclusion from this Cayley graph of H to this Cayley graph for G. Then a Cannon-Thurston map for the pair G and its subgroup H is a continuous map denoted I hat from the Cayley graph for H union its boundary to the Cayley graph for G union its boundary, so that this map extends the inclusion. So these maps were named after the work of Cannon and Thurston, who proved such maps exist for the fundamental group of a fiber inside the fundamental group of a closed hyperbolic three-manifold. And an interesting problem in geometric group theory is to ask for which pairs of groups does a Cannon-Thurston map exist, and if the groups are not hyperbolic, maybe for which boundaries does a Cannon-Thurston map exist. Mahan MJ, then Mitra, greatly extended the work of Cannon and Thurston to prove that if H is a normal subgroup of G and H and G are hyperbolic, then a Cannon-Thurston map exists. And moreover, in this setting, the Cannon-Thurston map restricted to the boundary of H to the boundary of G is surjective since H is normal. So there are two relevant examples of this theorem. The first is that a Cannon-Thurston map, the first is the result due to Cannon and Thurston, that a Cannon-Thurston map exists for the fundamental group of a fiber inside the fundamental group of the resulting closed hyperbolic three-manifold. And the second relevant example is that a Cannon-Thurston map exists for the free subgroup inside of a hyperbolic free-by-cyclic group. Cannon and Thurston proved that this map is finite to 1, and Kapovich and Lustig proved that the Cannon-Thurston map in this setting is also finite to 1. So these give naturally occurring examples of a finite to 1 continuous map from the circle onto the two-sphere and from the Cantor set onto the Menger curve. If the automorphism of the free group is induced by a homeomorphism is induced by a pseudo-Anosov homeomorphism of a surface with boundary, then the resulting group is not hyperbolic since it has some z cross z subgroup, but it is relatively hyperbolic. And as we heard earlier from Bena, there are a number of natural boundaries associated to this group, and you can ask if Cannon-Thurston map exists for these boundaries. And the answer is it depends on which boundary you consider. Bowditch proved that a Cannon-Thurston map exists for the free subgroup in this free-by-cyclic group with respect to the Bowditch boundary. Where in this case, the group is hyperbolic relative to the torus subgroup, and the Bowditch boundary is the two-sphere. On the other hand, these groups are also cat0 with the isolated flats property and have Sierpinski carpet cat0 boundary. And in joint work with postdocs at the Technion, Benjamin Beaker, Matt Cordes, who's here, Giles Gardam, and Radhika Gupta, who was here last week, we showed that a Cannon-Thurston map does not exist for the free subgroup in this free-by-cyclic group with respect to the cat0 visual boundary. So to reconcile these theorems, we note that the cat0 boundary sees the boundary of the flats. So we find two sequences of points that converge to one thing in the boundary of the free group, but once you include it in the free-by-cyclic group, these converge to different rays on the boundary of the flat. However, in the Bowditch boundary, the boundaries of all of these flats are collapsed to a single point, so this issue disappears. And I'll also remark that both of these results are more general than stated. MJ and Paul extended Bowditch's work to cover many normal subgroups of relatively hyperbolic groups, and we are hoping or wondering whether we can extend our work to hyperbolic normal subgroups of cat0 groups with isolated flats. So to summarize, our starting point to study boundaries of free-by-cyclic groups is the Cannon-Thurston map. And also important to us is the analogy between Cannon-Thurston maps for hyperbolic manifold groups and for hyperbolic free-by-cyclic groups. And we note that in the relatively hyperbolic setting, the strength of the analogy depends on which boundary you consider. So let me now explain what is the structure of the Cannon-Thurston map. For the free subgroup inside of a hyperbolic free-by-cyclic group, where we'll assume that the outer automorphism phi is atoroidal and fully irreducible. So I'll state the theorem and then explain it in a simple setting. So this is due to Kapovich and Lustig from 2015, using work of Mahan, MJ on ending laminations for normal subgroups of hyperbolic groups. They prove the following. They show that in this setting, the Cannon-Thurston map from the boundary of the free group to the boundary of the free-by-cyclic group factors as follows. So the Cannon-Thurston map goes from the boundary of the free group to the boundary of the free group, and it splits via a map called Q plus to the metric completion of the attracting tree for phi, union its boundary, and then to the boundary of the free-by-cyclic group via a map called R plus, and it also splits through a map called Q minus to the metric completion of the repelling tree for the automorphism, union its boundary, and then to the boundary of the free-by-cyclic group via a map called R minus, where the trees T plus and T minus are the attracting and repelling trees for the outer automorphism phi. The maps Q plus and Q minus from the boundary of the free group to the metric completion of these trees union their boundary are each onto the maps R plus and R minus from these trees union their boundary to the boundary of the free-by-cyclic group are each onto the maps R plus and R minus restricted to the interior of these trees are injective. And finally, the maps R plus and R minus have disjoint images when restricted to the interior of these trees. So these first bullet points are really due to Levy and Lustig from 2003. They prove that analogously to pseudo-Anosov homeomorphisms, which act on compactified Teichmuller space with north-south dynamics, a fully irreducible automorphism of the free group acts on compactified outer space with north-south dynamics and fixes two trees, T plus and T minus. In proving this, they define the maps Q plus and Q minus, and I'll explain these momentarily in a simpler situation. What the rest of the theorem says is the following. There are maps from the boundary of the free group, which is the Cantor set, onto these two real trees, the attracting and repelling trees, and then there are maps from the trees into the boundary of the free-by-cyclic group. And the maps on the interior of the trees are injective and disjoint. However, boundary points of the attracting tree are glued to points on the repelling tree, and boundary points of the repelling tree are glued to points in the attracting tree in such a way that the resulting space is the Menger curve. And one of our contributions is to understand how this gluing takes place more precisely. So before I explain that, let me give an example of the Q maps in the simpler situation that the automorphism is induced by a pseudo-Anosov homeomorphism on a surface with boundary. So the Q maps are essential for the analysis, and here is a simpler situation which gives intuition. So suppose that the automorphism of the free group phi is induced by a pseudo-Anosov homeomorphism of a surface with boundary. Then phi leaves invariant a pair of measured laminations on the surface, one attracting and one repelling, like this. Then the universal cover of the surface sits as a subset in the hyperbolic plane with infinitely many half spaces removed. And the laminations on the surface lift to geodesic lines in the hyperbolic plane, and I'll just draw the some leaves of the attracting lamination. So there are some singular leaves which carve out polygons and other lines which limit to these. And you see translates of this, so on. And note that the boundary of the free group is the Cantor set, which embeds on the circle in this picture. So in this case, the trees T plus and T minus have a nice description. The tree T minus is the dual tree to the attracting lamination. And the tree T plus is the dual tree to the repelling lamination. So in other words, to build the tree T minus, each complementary region in the universal cover is collapsed to a single point, as is each leaf. So this complementary region would correspond to some branch point with 3 directions corresponding to leaves. And each other complementary region gives some other branch points in the tree. So on. And then what is the Q map? So you pick a point on the boundary of the free group. And there are 2 possibilities. Either this point is the end point of some leaf of the lamination, in which case that point on the boundary maps to the corresponding point in the tree. Or you've chosen a point on the boundary of the free group so that the ray to that point passes through infinitely many leaves. And in that case, this point on the boundary under the Q map will map to some point in the boundary of a tree. And the other Q map is constructed similarly with the repelling lamination. And Levy and Lustig prove that an analogous situation holds for any fully irreducible automorphism of the free group. And also important to us is that in the attracting tree, leaves of the attracting lamination isometrically embed. So while they're collapsed to a point in one tree, they embed in the other. So in the remaining time, I'll first draw the construction of how we build some non-planar graph in the boundary using this structure theorem, and then I'll explain how we prove you can always find such a subcomplex. So here's the embedding. So we'll use the structure of the Cannon-Thurston map, which says that the Cannon-Thurston map from the boundary of the free group to the boundary of the free-by-cyclic group factors through these Q maps, Q plus and Q minus, to the attracting tree union its boundary, and to the repelling tree union its boundary. Okay, so to build the K33 subgraph, we use essentially 3 leaves. So these will all be leaves of the attracting lamination. So we first choose some singular leaf, drawn in yellow, which embeds in the tree T plus, and therefore embeds on the boundary. And in the other tree, it maps to a single point. The boundary of these leaves map to a single point. So, and we use two other leaves, one in red, which again maps into the attracting tree and to a single point in the repelling tree. And we use a final orange leaf, which is similar, which maps into the attracting tree and to one point in the repelling tree. And the key point, but subtle point, is that we can choose these leaves so that in the repelling tree, these points are not collinear. And this is exactly what would not happen if this was realized as a lamination on a surface. So if you were to map this to the repelling tree of some automorphism induced by a surface homeomorphism, then the points corresponding to these three leaves would be collinear, exactly as they cut the hyperbolic plane up. And we prove you can find leaves so that this does not happen if the automorphism is atoroidal and fully irreducible. So once we have these leaves, we can now build the subgraph and just tell you the vertices. The center of the tripod maps in as the first point. The boundary of the yellow leaves are all identified to the point in the second tree, that's point number 2. And the boundary of the red leaves are point number 3. We use the boundary of the orange leaves in a moment. And the other 3 points in the K33 subgraph come from these branch points. So you see that since this tree embeds on the interior, the point 1 is connected to vertices A, B, and C. The point 2 is connected to vertices A, B, and C. Point 3 is connected to A and B. So you can build some non-planar graph using just one tree, and to make the connection from 3 to C, you have to use this path in the other tree, avoiding point number 2. So you go via 4. And there's some non-planar graph in the boundary.
How did you choose your leaves? How did you know that would work?
How did we know that would work? Trial and error for a while. So I will explain how we know we can find these leaves once you know such a configuration would be all you wanted if you could find them. So the main challenge is to prove that for any fully irreducible atoroidal outer automorphism, you can find 3 leaves of this type. And the technique to do that is to use the band complex associated to this free group automorphism. So I think this was introduced by Rips to study groups acting on R trees. And in this iteration for compact subtrees, the results I'll state are due to Poubois, Hilion, and Lustig. So I'll describe the band complex associated to the repelling tree T minus. So this is some real tree, so on. So they prove there exists a compact subtree K of T minus with a set of very nice properties. So suppose K is this thickened, slightly thickened, compact subtree. They prove that for this subtree K, so as in the case of a surface group and its dual trees, the free group acts on the repelling tree for a fully irreducible automorphism of the free group. And they prove that each generator of the free group induces a partial isometry of the subtree K. That is, for each generator, say x1, there's some subtree of K that xi maps to some other subtree contained in K. So for each generator, it's not mapped off of K, it's mapped into K. And from this data, you can form the band complex by attaching bands. So in other words, for each generator of the free group, you attach a band where this band is isometric to the subset of the tree times the interval, where one end of the band is glued to the domain of the partial isometry, and the other end of the band is glued to its image. So maybe x1 gives rise to this band, where for each point in its domain, you can follow along the band to its image under xi. And you do this for each of the n generators of the free group to form some complex. So this is in analogy to an interval exchange transformation for a pseudo-Nassau homeomorphism. And similarly, it carries a lot of important information about the free group automorphism. In particular, there's a natural foliation of the band complex, where each point on the, where leaves correspond to points on the tree and their image under the bands. And the band complex has a natural foliation, and so does its universal cover. And in the universal cover, leaves correspond to leaves of the attracting lamination. So for each leaf in the universal cover of the band complex, these are all now undone. Each leaf corresponds to some leaf in the attracting lamination. So this is a very useful object for us because it allows you to visualize both leaves in the attracting lamination, which are lines in the attracting tree, and the repelling tree at the same time. Moreover, if you have a leaf in the attracting lamination, its image under the Q map is exactly this point in the subtree T minus. So this is really useful object to study both laminations at the same time. And one procedure you perform to band complexes is Ripp's induction. That means if you ever see a band, if you ever see a sub-segment of the tree that's contained in only one band, you remove that band and continue and continue and continue. And we prove that for either the attracting tree or the repelling tree, at every step of Ripp's induction, you can find 3 bands, say one in red, one in orange, and one in yellow, which all overlap. And you can find this at every stage of the induction. And this has two consequences. The first is, from this picture, it's not hard to prove you can find leaves with these properties. And the second consequence is that this demonstrates the difference between a fully irreducible atoroidal automorphism and some automorphism induced by homeomorphism of a surface. There, after performing Ripp's induction, you essentially arrive at an interval exchange transformation with no overlapping bands. So this is this difference in dynamics is exactly what allows us to construct some non-planar subgraph in the boundary. And I'll end by saying that the goal and challenge of this project was to try to find some properties of all atoroidal, fully irreducible free group automorphisms that lead to some topological construction in the boundary. And now I'd like to do the opposite, which is to understand which properties of free group automorphisms will allow you to distinguish boundaries once you add additional structure, quasi-conformal structure. Thank you.